This research proposes a deep latent state space generative model to capture interactions among correlated clinical events, such as kidney failure and mortality, in healthcare. The model explicitly models temporal dynamics of patients' latent states, enabling accurate estimation of survival distributions. A new discrete-time formulation of the hazard rate function is developed, providing flexible fitting of general time-to-event distributions without restricted parametric assumptions. The model leverages electronic medical records, EMR, time series data to jointly predict mortality risk and capture organ failure risk trajectories, identifying temporal correlations among multiple clinical events. This provides clinicians with a comprehensive picture of a patient's medical condition. The deep state space generative model captures interactions among observations, interventions, critical event occurrences, latent patient states, and their uncertainty, contributing to the technical significance of the field. The paper reviews related studies, combining a deep state space model with a discrete time hazard model to support more flexible distribution models and provide better interpretations of the influence among events. The correlated time-to-event prediction section formally defines the learning task, utilizing EMR time series data to predict the time of future critical medical events and estimate the distribution of time duration between the time of prediction and event occurrence. The proposed deep state space model generates a time-calibrated multiple event risk trajectory, capturing the risk of different clinical outcomes over time. This model integrates patient physiological states, observations, and interventions, allowing for predictions of time-to-event distributions for various clinical events. The model uses a Gaussian state space model with a discrete time hazard rate function, dependent on the dynamic latent patient physiological state at each time step. The learning objective and associated variational lower bound support the time-to-event prediction task, with the evidence lower bound, ELBO, of the log event time likelihood derived to estimate time-to-event distributions in ICU patient care. The proposed deep state space model, DSSM, is designed to predict time-to-event outcomes in temporal event data, comprising a loss function with log likelihood and regularization components. The model architecture consists of an encoder network, state transition module, and hazard rate emission module, trained using stochastic gradient descent. The DSSM is evaluated on the MIMIC dataset, predicting the risk of in-hospital death and 4 types of organ failures, with performance evaluated using the Syndex, OCROC, and AP metrics. The model demonstrates better predictive performance for time-to-event prediction and uncovers meaningful insights about latent correlation among different event types. The dataset's missing values are handled using imputation methods, and the model's performance is evaluated within 2 fixed prediction windows, 0, 24-hour and 0, 48-hour, showing good discriminative power and accurate prediction of event risks. The DSSM outperforms state-of-the-art methods, DeepServe and DRSA, in terms of AUCROC and AP, particularly in short-term predictions. The model's ability to predict hazard rate trajectories is demonstrated, accurately capturing true event times for observed and censored events. Correlations between mortality and organ failures are revealed, with varying levels of correlation observed across patients and organs, quantified in Table 2. The proposed model provides valuable insights into patient condition progression, supporting clinicians with better decision-making, and demonstrates potential as a powerful tool for healthcare providers. Equations and algorithms used in the model include the log likelihood loss for time-to-event prediction and regularization loss, as well as the stochastic gradient descent algorithm for training. Figures 5 and 6 demonstrate the model's performance in predicting hazard rate trajectories and revealing correlations between mortality and organ failures. Table 3 presents the model's performance metrics, highlighting its potential as a valuable tool for healthcare providers. This research introduces a deep latent state space generative model to capture the relationships between patients' mortality risk and associated organ failure risks. The proposed model, demonstrated through extensive experiments on the MIMIC dataset, outperforms several state-of-the-art baselines in terms of prediction accuracy. It provides meaningful insights into the temporal relations among multiple types of events, demonstrating correlations between different organ failures and mortality risk. The model's predictive performance is presented in Table 3, showing higher Syndex and AUC at 2-4 AUC at 4.8, AP at 2.4, and AP at 4.8 values across various organ failure types compared to baseline models DRSA and DSSM. A comprehensive review of related work and survival analysis is also provided, listing 36 references that have contributed to the development of the approach. The supplementary materials detail data preprocessing steps, including code harmonization, unit conversion, outlier removal, and value normalization, as well as the features and their units used in the experiment. These include access pressure, albumin, ALT, anion gap, AP, arterial base excess, and other measurements. The proposed framework incorporates a comprehensive set of features to capture the complexities of mechanical ventilation in critically ill patients. Table 6 presents the intervention features and their corresponding units, which include various mechanical ventilation settings and parameters such as dialysate rate, fraction of inspired oxygen, positive end expiratory pressure, peak inspiratory pressure, respiratory rate setting, and tidal volume setting. The framework's predictive model, based on a combination of machine learning algorithms and statistical techniques, is designed to handle the complexities of the data. The model's performance is evaluated using metrics such as AUROC, AUPRC, and MSE, demonstrating the model's ability to accurately predict patient outcomes with AUROC values exceeding 0.9 for mortality prediction. The framework's predictive capabilities have significant implications for clinical decision-making in the ICU, informing the development of personalized treatment strategies and potentially leading to improved patient care and outcomes. However, the framework's limitations include reliance on high-quality data and the need for further validation in diverse patient populations. Future work will focus on addressing these limitations and exploring the application of the framework in other critical care settings.